this position is 3. So this function also discontinuous at the number 2. Okay, this discontinuity is a removable discontinuity because we can define the value of the function at 2 be 3. Will be make it continuous at 2. Also, this discontinuity is a removable discontinuity because we can redefine by replace 1 with 3 to make this function continuous at 2. Okay. So the discontinuities of these two functions are the same type, removable discontinuity. Okay. C. So this is a rational function. It is continuous on its domain, namely the entire real number line except at the 0, at the origin. Okay, the graph of this function looks like this. Since this function is discontinuous at 0, because the limit of this function is 0 does not exist. Does not exist. So it is discontinuous at 0. And it continues at every point other than 0. Does not exist. But the behavior of this function at 0 goes to infinity. So this discontinuity is an infinite discontinuity. An infinite discontinuity. Okay, at 0. D. The function f now is the greatest integer function. Greatest integer function, this symbol stands for the greatest integer of x means the value of f at x is an integer, which is less than or equal to x, but the largest one. The name of this function is the greatest integer function. Means the largest integer which is less than or equal to x. And we read this one, the greatest integer of x, whose graph is between 0 and 1 is 0. Jump. A jump. And a jump. 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 So, as we have seen before, this function local in each interval or a half open interval, a constant function, a constant. So this function f is discontinuous at each integer, for example, n integer. In fact, when x approaches n from the left, for example, if n is 1, from the left is n minus 1. Approaches n from the right, for example, 1 from the right, it is the constant, a part of this constant function 1. They are different. Therefore, this kind of discontinuity is a jump. Discontinuity, okay, the jump discontinuity. See, jump. Because one-sided limits exist, but different. So sometimes we give some phenomenon, some name is easily to follow. We don't need to explain something again, use very elementary statements, because we already have some concise terminology. 比如说，我们有时候呢，给一些专业的术语定义之后，会很方便谈论事情。一讲这个名称，大家都明白了，都明白。不用每次又解释，你看看左极限存在、右极限存在又不一样，所以不必每次都用很粗本的语言来说明。你可以慢慢用一些名称使得程度变得高阶的语言啊。So if we know some, quite a few terminologies, so we don't need to use the very elementary statements. We can use some advanced statements to describe some fact or some theorems. Well, this is example 2. Next, example 3. Oh, example 3, exactly this one. So, to example 4. Okay, example 4 show that the function f of x is continuous on the interval, the closed interval -1 and 1. Now, this is a set, an interval. Some point of this set is interior to this set, interior point of this set. At that position, we need to consider two-sided continuity. But at -1 and 1, the end point of this interval, we have to consider one-sided limit, okay, or one-sided continuity. So we divide into 3 cases. Let A be any number in this set. Case 1, if A is interior to an interior point of this set, this interval, or A between -1 and 1, then we have the limit of x approaches A, f of x equals x approaches A, 1 minus the square root of 1 minus x squared. Because A between -1 and 1, same as the absolute value of A is less than 1. So, the limit of x squared. But this one, yes, polynomial is continuous. At A, this is A squared. It's less than 1, so 1 minus A squared is a positive number. By lambda theorem, this limit can be evaluated by direct substitution. By definition, if a function whose limit at some number A equals f of A, f is continuous at A. Okay, so f is continuous at every interior point of the closed interval. Next, we consider endpoints. There are 2 endpoints when A equals the left endpoint. We will consider the limit from the right. Okay. From the right means more close to more close to 0 than -1. So the absolute value of x should be less than 1, and this square is less than 1, so this value always positive. And when x equals -1, this is 0. Since the square root function is continuous from the right at the origin, this is 0. Therefore, f is continuous from the right at the left endpoint, case 3, when a equals +1. Similarly, this time we consider approach 1 from the left. Again, if x approaches 1 from the left, means x is always less than 1, and this one must be a positive number, always defined, and goes to 0. Therefore, f is continuous okay. By case, all cases, we have conclusion. Can we conclude? F is continuous on this interval. Okay, so just by definition, you can check. If interior to this interval, we have to consider two-sided continuity. If at endpoints, you have to see a right endpoint or left endpoint. If a left endpoint, we consider right continuity. Right endpoint, we consider left continuity. So it seems it's nothing. It just takes time to absorb this knowledge. 这是没什么，我们只要花点时间去吸收 absorb 啊 absorb。Say it again. By definition, if a function is continuous on a set, on an interval, you have to, by definition, this function is continuous at every number in that interval. For this kind of A is interior to this interval, so we have to consider both sides. Two-sided limit, if A is here, inside. So we have to consider two-sided limit. Since this one equals this one, by limit theorem, we have learned before. This is exactly the definition of f is continuous at A. And case 2 and case 3, we consider endpoints or boundary points. We can only consider one-sided limit. One-sided limit. And this shows, yes. So, in summary, this function is continuous at every point of this set, this interval. By definition, f is continuous on this interval. Okay? Okay. Take a break.